The next question for us to consider is, how do we go about finding the x values where a function has a vertical asymptote? And the short answer is that basically a function will have one of these vertical asymptotes at x equals c if when you take the limit as x approaches c, when you get something like n over 0. So if you get 3 over 0, or if you get 5 over 0, if you get any non-zero number over 0, if you can find a limit that results in that, we're going to end up with a vertical asymptote. I mean, the video that we just talked about gave the idea that, we can't actually compute 3 over 0, but as we approach 3 over 0, we get huge numbers, which result in a vertical asymptote for a function. So if you're looking for where a function has a vertical asymptote, you're looking for where there's division by 0, and where the limit looks like this. So if you like to have specific steps, these are your steps. Step 1, determine all of the x values that will cause division by 0. Right? So the way that we're going to do that is we're basically going to set the denominator equal to 0, and we're going to find all the x values that will cause division by 0. Then, not all of those will necessarily be vertical asymptotes. For each one of those values, we want to find out if the limit exists. And there are two possibilities. If the limit exists, sort of think about that graphically. If the limit exists, it means that the two sides of the function must have come together, which means that there's no asymptote, right? It means there's probably a hole there, right? On the other hand, if the limit is of the form n over 0, in other words, if the limit doesn't exist, and you get, 3 over 0 or 5 over 0, n over 0, it means you have a vertical asymptote, right? So here's my first example. I want us to determine the vertical asymptotes of this function, right? So I had mentioned that the first step that we want to take is we want to set the denominator equal to 0, and we want to find out what our potential vertical asymptotes are, right? So we want to find our potential values. So that will be when x squared minus 4 is equal to 0. I can factor that as x plus 2, x minus 2 equals 0. And that basically means we have x equals negative 2, and we have x equals positive 2. These are my potential vertical asymptotes. They're not necessarily the vertical asymptotes, but these are the potential ones. So now we need to determine if these are vertical asymptotes. We need to determine if they're asymptotes by looking at the limits. So I'll go ahead and write out both of those. We will have the limit as x approaches negative 2 of x minus 2 over x squared minus 4, and then we'll also have the limit as x approaches positive 2 of x minus 2 over x squared minus 4. Now, it should be fairly clear. What we can do here is we can sort of just evaluate both of these. And actually, I'm going to remind myself, the way we do limits is we attempt to evaluate the expression for the given value. So I'm going to try just plugging in negative 2. When I do that, this first one gives me negative 4 divided by 0. And so right away, I got something of the form negative 4 over 0. And that means that this function has a vertical asymptote at this value. We should go ahead and look at the other one as well. There may be a second vertical asymptote, the other one may not be. So for this one, again, I'm going to attempt to evaluate the function for the value that was given. When I try and plug in 2, I end up with 0 over 0. And that doesn't mean anything. It means try harder. It means we don't know what the limit is, so we need to investigate further. So I'm going to go ahead and sort of do the limit the way that we would have done before. We'll factor this. We'll have x plus 2 and x minus 2. We notice here that these cancel out. Leaves me the limit as x approaches 2 of 1 over x plus 2. And now when I attempt to evaluate it, I end up with 1/4. Right? So in this case, the limit did exist, and that means the function does not have a vertical asymptote at x equals negative 2. In fact, what I would say is, since this limit exists, it means this function has a hole. And we can even give the point where the function has a hole. We know that this function actually has a hole at the point 2, 1/4, because I know the x-coordinate is supposed to be 2, and the y-coordinate that we're getting really close to is 1/4. So it makes sense that that's where the function would have a hole. So the actual answer to the question was that this function has a vertical asymptote only at x equals negative 2. This was just sort of extra information that we found out along the way. So I have one more example that I'd like you guys to try on your own. So take a minute or two, pause this video, work through and find out where this function has vertical asymptotes. So just like we did before, we start by finding the potential vertical asymptotes by setting the denominator equal to 0. x squared plus 2x minus 3. So let's see if we factor this as x plus 3 and x minus 1. So we end up with x being negative 3 and x being positive 1. Alright, so now that I have these potential vertical asymptotes, my next step is to look into the limits. Let's see whether the limit exists for these two values. So I will look at the limit as x approaches negative 3 of my function, 3 minus x over x squared plus 2x minus 3, and then I'll also look at the limit as x approaches 1 of 3 minus x over x squared plus 2x minus 3. Okay. In both of these cases, we remember that we're supposed to try and evaluate limits by attempting to evaluate the expression for the given value. So when I attempt to plug in negative 3, I end up with 6 over, in fact, I think I'm going to run out of space there. I'm going to end up with 6 over 9 minus 6 minus 3, so that's 6 over 0. So right away we can tell that we have a vertical asymptote at x equals negative 3. We'll now look into the other one. For this one, again, I'm going to attempt to evaluate the expression for 1. So when I plug in 1, I end up with 2 over 1 plus 2 minus 3. Sure enough, we end up with 2 over 0 again, and so this means the function has a second vertical asymptote. It also has a vertical asymptote at that x value, at x equals 1. And that's it. We found these two vertical asymptotes. There are no other places where we might have division by 0, so these are the only places that this is going to happen. So in summary, we look for vertical asymptotes for where the denominator is 0, and also where the numerator is not 0. Those are the things that cause the giant growth in the values of the function that are necessary to create a vertical asymptote.